1. Does anyone have any questions on the homework? All right, the example we left off discussing, we were kind of revisiting the idea of these initial value problems. And so we said there's two ways we can solve this. We were given a velocity and we wanted to find the position. So we said we could just go through the standard antiderivative process, use the initial condition to find C. Or we could use the fundamental theorem of calculus method, which required us remembering this formula. So we'll look at this method and then see that both methods give us the same result. So we are given S of 0. I believe that was S of 0 equals -3. Is that it? Yeah. So we are given S of 0 as -3. We do need to compute the integral here. So we have the integral from 0 to t on our velocity function. 32 minus 2t squared. Or sorry, I'll use x since the upper limit is t. We just want those variables to be different. Whatever we have up here in our upper limit of integration, that's going to be our ending variable. So if you want a function of t, you want a t up there. If you want a function of x, you want an x up here, and so forth. So we're just going to integrate this. And whatever this turns out to be, that is our position function s of t. Remember, since we're integrating this, it's worth pointing out we do see instances like this sometimes, but since we're integrating with respect to x, that this upper and lower limit of integration are x values. So we have -3 antiderivative, you get 32x minus 2x squared, or sorry, 2x cubed over 3. Evaluated from x equals 0 to x equals to t. And so 0 in there is just going to zero everything out. T in there is going to give us what we need, and then we can compare to our previous result. It'll just be written in a different order. That's it. So we have -3 plus, and I'll write this out again. According to the fundamental theorem, we have 32t minus 2/3 t cubed. There's our f of upper limit, antiderivative at the upper limit, minus the antiderivative at the lower limit. So that's the same as the above result. We have -3, 32t, and minus 2/3 t cubed for s of t. So we see that either method is giving us the same result. Just be careful. Sometimes the instructions will ask, do it this way versus the other way. Okay. Yeah.
Do you care on like a test on how we order our items in the answer?
No,
Okay.
no. As long as it is the same, right? So addition, subtraction, doesn't matter how we add those terms or multiply terms. So I'm not picky on that. Yeah. Any other questions on that example? So the next example is similar. It's kind of an extension of what we just did, but the main idea here is that whether we're given a velocity function and they ask us to find position, we have two methods to do so. But same is true if we're given acceleration, we can find velocity and then we can find position using either or. So, in all honesty, I think we'll skip that example. It's pretty straightforward. So, similar to last example. So just if you're wanting to check, I'll write the velocity and position functions here, plus 20. And then position. So if you want to work that, and maybe try both methods so you're familiar. There are some examples where I think it's more convenient to use one method over the other, and in our example 9, we'll see that. But this idea where we're working specifically with velocity, position, and acceleration can be generalized to just whatever quantities we're dealing with. So position, velocity, displacement stuff is over here, but general problems are here where Q is just some quantity and Q prime is the rate of change of that quantity. So they've kind of paralleled the specific to the generic. So notice instead of displacement, we're calling that just a net change in whatever quantity you're dealing with. And then future value was just equivalent to what we just did, where it said, hey, here's the derivative of the quantity, the rate of change of the quantity. Find the function that describes the quantity at any point in time, referenced as future value. Okay. So I think since we've worked with position and velocity functions, if we make the parallel over to the general statements, the notation a bit different, but the principle is still the same. So we'll kind of take that into the next example, where at t equals 0, a population of a town was 250 people, and then during the following years, the population grew at a rate of p prime of t equals to that function. So they're giving us a growth rate function, not a population growth rate. And then, so the question is, what is the population after 20 years? Well, in order to determine the population after 20 years, we need a population function where we have the rate of change of the population function. So again, it's like starting off with, hey, here's a velocity, what's the position? Does that make sense? Hope that's pretty clear. Okay, so there's really one of two ways to do this. You see part A and part B. So in part B it says find the population at any time. So we could just find the population function, through finding the antiderivative and solving for C. And then once we have that function, we go back up to part A and plug 20 in. Or we could just say, well, according to the formula, let me rewrite that. And this is that last one on the previous page. So we want to know what is the population after 20 years. We want to know P of 20. But we know that that's equivalent to the initial population, P of 0, plus the integral from 0 to 20 on the rate of change function, P prime of t. And so we can find the population after 20 years that way as well. Does anyone have any questions on that? Just again, reference this very bottom one here. So we have our population is at future time is population initial plus the integral from 0 to t on P prime. All right, so we just need to compute that integral. Initial population is given. All right, so what would the antiderivative be? Yeah, go ahead.
Well, pouring out 30 in front of the front, it would be t plus 2/3 times t times t to the 3/2 power.
Okay. Some people prefer to leave the constants in. That's fine as well. Okay, so bottom limit in there, that's going to zero everything out. We're just going to plug 20 for t and t to the 3/2. Multiply that by 2/3, add everything up. Sorry, I forgot my plus here. So you should get 2638.85 as the initial value. And probably what we would say is that there's about 2,638 people. We wouldn't round up to the nearest person. It would probably make more sense to round down to the nearest person. So that's what we'll say after 20 years. Whatever, if it references a town, I'll just say the population. people. So, the overarching theme here, once again, is if we have some rate of change, even if the quantity is unknown, if we have a rate of change of that quantity and the initial value of that quantity, then we can get back to the actual quantity. And so find the population P of t at any time. We can look at this in one of two ways. We have the antiderivative method or the fundamental theorem method. So maybe we'll just look at that one, the antiderivative method. So we're just going to say that P of t is the antiderivative of our population function. And use our initial population to find the constant. So we did already find that antiderivative in the previous problem. Either route you take, you'll still have to find an antiderivative. So we have 30. To the 3/2 plus C. You know, and the constant's going to get affected depending on whether you put the 30 in with every term before you integrate, or find the antiderivative, or if we leave it out here, once we multiply this 30 by this C, it's going to turn it into another C. So you might just want to keep track of your constants. It's still going to be another constant at the end of the day. It's still going to be C, right? But once we get to chapter 9, you have to keep track of those constants from antiderivatives a little bit, keep up with them a little bit more carefully. Okay, so this is our P of t function. We need to find C. So we're going to use the initial condition and say, well, I know P of 0 is equal to 250. But P of 0 is also 30 times 0 plus 2/3, 0 to the 3/2 plus some constant, let's say. All right. So what we have is, we've got 30 times our constant, equals to 250. See, what did we mess something up? Does that look okay? 30. Did we write that function down? 30 plus 2 to the 1/2. Yeah, okay. 30t 2/3 3 plus some constant. Looks fine. Looks okay, right? Well, what do we have? C1 is 25 over 3. No, I guess we can leave that. Well, because let's look at it this way. If we put it back in here like that, remember that C1 is going here. This, and we have all of this stuff times 30. So when we multiply that back in, it might be a little bit more advantageous to use a denominator of 30 because it'll cancel this out right here. If we were to distribute that 30 all the way through at the beginning, you wouldn't have ended up with the funky fraction. Okay, so we have P of t. We'll just simplify this once we plug that in back into our function for C. Which means that the position function at any time, we've got 30t plus 20t to the 3/2 plus 250. And you could also try the fundamental theorem route just to verify that you do end up with the same thing. But again, we could have said, well, in order to answer part A, I need a population function to evaluate at 20. So we could have just done this first and then plug 20 into this to get our answer from part A. So it's kind of the basic idea of 6.1. We do see, actually it's the only other physical application section in this course later on in chapter 6. Everything else is pretty much mathematics, but that's kind of like our only physics section that we see. What do we have next? Okay, just a general summary here. All right, so just try to work on some of the homework this weekend. To be honest, some of the problems in the homework we didn't cover exactly. So the idea is that maybe they're a little bit more challenging than some of the problems we did. Not all of them, but one or two. So just try those without, the help feature. And if you have any problems ever with the homework, I don't mind going over some of those in class as well. Just curious, was anyone here not in class? When was that? Thursday? Tuesday? No? So this. I'm going to hand you out 6.2. Remember, after 6.2, if you want the notes, you need to start printing those beforehand.
How often do you change up the notes from what's already kind of been going through all right now?
What do you mean, like these blank ones?
Yeah, in case we want to like print out way ahead.
I don't. Like,
So we can just print all the notes like tonight?
well, I guess. I'm not infallible, so I do make occasional mistakes. But if anything, it's not going to be like, oh, we weren't supposed to cover that problem at all in this section. I'll just, cross it out and write something in. So yeah, I guess if you want to print all of them, go for it. So as we mentioned last class, this is something that, in theory, you should already know. I understand that some of you didn't take Calc 1 here, so you might not have seen regions between curves, but I don't think that we'll cover every example that we have here. So just as a reminder, when we looked at Riemann sums, and this idea that is pertinent to Riemann sums sort of follows us through the next two sections, including this section. So when we always looked at some function from A to B, and this is our x-axis. So we always looked at the function to the x-axis, and then we said, what's the area of that region? So the basic idea there was, we said, well, let's cut this up into into really small but manageable pieces. And every time we made a cut through here, we were making a rectangle. So we said we can certainly manage the area of a rectangle. And then once I have all of those rectangles in there, then I can just add that area up of all rectangles, and then I'll have the area of that weird shape right there, right? So sometimes it's referred to as the slice and sum method, where you just slice it up and then you sum all of that stuff up. That's essentially what we've done. The only issue we had was fitting this region up with, I guess, infinitely many rectangles, but then that's where the limit came in, to give us infinitely many rectangles in that region. So we said, all right, well, let's let the let the length of each rectangle be uniform and call it delta x, and then this value here. There's some like particular notation, but we'll say that this is x, so that height of the rectangle is f of x. And then we said, well, we want to add up, I think they call that k equals 1 to n. So we added up like a finite number of those. Sorry, that's improper. It said x sub k, so we'll call that x sub k right there. And what that was just the height times the length of the first rectangle, and then we added to that the height and length of the next, right? So there's us adding all of these slices up, and then we said to get an exact area, we have to let the number of rectangles go to infinity. Do y'all kind of remember that? Yeah.
Real quick question. So
Sure.
sometimes it says to sum Riemann like from the left.
Yeah.
Or like, so I just super clear. The wording is sometimes confusing. So when it's like a left Riemann sum,
Mm-hmm.
do you go up and then move to the left, or is it?
Yeah, so the terminology with left, right, and midpoint, often Riemann sums, all that had to do was with which part of each rectangle do we use to evaluate the height. So like if I had this right here, and I said, oops, let me just draw this a different color, and I said, here's like a rectangle, let's just fixate on that one. And I said use the left Riemann sums. Well, for all of those rectangles, we're going to use the left endpoint for determining the height of the rectangle. If we had, another one over here, and it's, well, let me scoot that over, and we said use the right Riemann sum, then we're using the right endpoint to determine the height. So that's really the only difference. For us, left, right, midpoint, whatever Riemann sum, it doesn't matter, because that limit as n goes to infinity. So as we force infinite amount of rectangles in there, whether we're using the left or the right, they all become like lines, basically. So it's irrelevant, but that's what they mean when they say that. Okay, so then that's how we defined a definite integral. We said, I know this notation is weird, but delta x, this right here, is the same thing as what we wrote, because if delta x, the length of each rectangle, goes to 0, right, then that means we're putting infinitely many of the rectangles in there. Delta x approaching 0 is equivalent to saying n is approaching infinity in this context. And that's how we defined a definite integral. That was the very definition of what it means to compute a definite integral. And the nice thing about these is that it was always the function and the x-axis. That's all we ever had to deal with there. But we're shifting our focus here in 6.2 to a more broad picture. So instead in 6.2, what we're looking at is, like a function f of x and another function g of x. And we're going to ask, what's the area between those two? From a to b, what's the area between those two functions? But the idea of how we compute that area is still exactly the same. We just take a bunch of rectangles and slice that up, fill that region up with infinitely many rectangles, and then that's your area. And add those up, that's your area. So for simplicity, we're still, again, we're going to call this delta x for, you know, the, I guess, what are you ever going to call that? The length or the width of the rectangle? Maybe width, I guess. We're still, all of them are still going to be delta x. But this time, let's go back up here just so we can, all we're saying is, well, how far off the ground, basically, is this right here? Another way to think about this is we're just taking the distance from the function to the x-axis, which gives us that the height of that rectangle. It's the same idea. In order to measure the height of this rectangle, it's easy when I know, like, what if this y value here was 8 and this y value here was, I don't know, 5. Then the height of this green rectangle is 3, right? That's very straightforward. But again, the problem is both of those y values are varying throughout. So what do you think we're going to do? How do we calculate the height of that rectangle?
Subtract f of x from g.
Yeah, we just take, again, let me do that specifically. If I just wanted to know what the height of that was, you just take 8 and subtract off 5, right? Well, that's how we would do that all the way through. So let me label this, you know, this is the h that we're trying to measure. The height of each rectangle is just given by, here, f of x minus g of x. But maybe more, I guess more generally speaking, we could interpret that as the top function minus the bottom function. Okay, so now what we're looking at is summing up all of the rectangles whose height kind of, I guess initially it's going to look like f of x something. So those are the rectangles' heights, and here are their lengths. So when we multiply those two, we get an area, and we're going to add all that up again. And let the number of rectangles go to infinity. And again, this thing right here is directly related to that definition, so it turns into a definite integral. So that's equal to the integral from a to b, f of x minus g of x dx. So that's how we compute the area between two functions. Scoot up a little. So are there any questions on how we're doing that? All right. It's also worth mentioning, even though you didn't do this when we were finding areas under curves, that we could have, we can and will integrate with respect to y, not just x. So let's call that function c of y. I don't know, and b of y. The same idea here is present. We're going to draw our rectangles like this. I'm just overemphasizing a rectangle. But this time, what would we call the, I guess, width of the rectangle, or right here, what would we call that? delta y. And so this idea of, notice here when we have these horizontal rectangles or horizontal slices, that we're going to be dealing with dy, which means that we're integrating with respect to y. So everything needs to be in terms of y, right? When we have these vertical rectangles or slices, then that's indicating that we're integrating with respect to x. So that becomes a huge issue in 6.3 and in 6.4. It's really one of the most important things in setting up those types of problems that we see is knowing which variable to integrate with respect to, because then that tells you which other variable you should solve for and all this other stuff. Okay, so our vertical slices dx or horizontal slices dy. So this will just take the form, the area is the integral from, and let's, for argument's sake, we'll say that these are different bounds. Let's say this is like alpha and this up here is beta. Right? So we would just integrate from a y value of alpha to beta. So since we're integrating with respect to y, again, the bounds need to be in terms of y values, not x values. So alpha to beta. And then how would we calculate the height, if you will? How do we calculate the height of each rectangle here?
C of y minus b of y.
Yeah. So it's the right curve or the right function of y minus the left. So here what would we have? C of y minus b of y. So right minus left. So what would the reason for that be, to be? Why would we have, or why would we want to be able to do either or?
Sometimes you might know the position of like the x bounds but not the y bounds, or the y bounds and not the x bounds, so you have to solve it that way.
Okay, like in what situation are you thinking? Like you would know one but not the other?
Like just the
Okay, I mean it's definitely you're on the right track. It's definitely has to do with like the ease of the bounds, but the bounds also depend on the region, which I guess I'm really looking for something more specific, but it's not that you're wrong. Yeah.
Sometimes like the top function like switches. So like maybe in one case C of y would be above b of y, but then at a later point b of y is above c of y.
Okay. Yeah, certainly a possibility. We could have, the functions kind of switching. Like this is the top function and then it's the bottom function. Then we have this other function like this, right? So here, the top function kind of becomes the bottom function and the bottom function becomes the top, right? But if we knew this as a function of x and we knew this one as a function of g, and g as a function of x and f as a function of x, then we could just continue on with integrating with respect to x. Even there, we would just have to kind of parse it out, right? It's not necessarily for that either. Let's give someone else.
If you don't have a line or if you have a line that's not a function.
yeah.
Like, what do you mean?
So like if it has two y values for one value of x.
Okay, so like you're thinking of maybe like an ellipse or a
Yeah.
circle or something like that. Yeah, on the right track. I'll give you a hint. Maybe think about like when we did implicit differentiation in Calc 1. did you want to add? Yeah.
Between different trig functions and like do it in between them and they change. That's why changes.
Well, then that would kind of be in this situation. We would still be in this situation here. So like those, if we knew like a function of x or y or whatever, you know, we would still be able to work with that. Yeah.
I'm just looking at what you drew for the, in regards to y,
Mm-hmm.
and for at least a portion of that, b of y, if we took it in regards to x, that function would be both the top and the bottom. So I feel like that would be the situation where if you have part of it is just one equation, it's both your top and bottom.
Yeah.
And then you switch to the other, it might just be easier to switch to the y-axis instead of in regards to the x.
Right, right. And sorry, what was your name? Patrick, is that kind of what you were meaning?
Yeah.
Yeah, okay, that makes sense, right? Because like even if I looked at a simple, like if I looked at x equals to y squared, you know, we know that thing looks like this. But if I said, you know, like integrating this with respect to x, like here's my rectangle with its length dx, then we would say, well, it's, you know, I can't say y squared minus y squared, right? I can't integrate y squared minus y squared, I mean, just for argument's sake, with respect to x, right? And if I did, it's not telling me anything, because 0, I know the height of that rectangle isn't 0. So, yeah, that's more or less on the right track. The reason I brought up implicit differentiation is because there are functions like, you know, maybe b of y is a function of y. We just don't know how to solve for x, or we can't solve for x, right? So if we said integrate this with respect to x, then you look at the function and say, well, I can't solve for y. You know, maybe it's, you know, maybe this function is something complicated like sine cubed of x times y squared plus xy equals to 3 or something like that. You know, it's not possible to solve for x. So then we would say, well, if I can't solve for x, I wouldn't want to integrate that or put that into the problem. I want to leave everything in terms of y. Maybe that x is not there. Maybe it's on the other side. But it's to avoid those kinds of issues where you wouldn't see that. But it's to avoid the issues where we couldn't solve for one of the variables. Maybe you can't solve for x, or maybe you can't solve for y. Okay. And the other reason is at this point, it's not as obvious, but at this point, we don't have a lot of integration techniques, so there's not a whole lot of functions we can actually integrate. So if you look at, you know, if you looked at, for instance, a simplistic, more simplistic approach is like if y were the inverse sine of x, you know, we couldn't integrate that, right? We don't know how to integrate the inverse sine of x. However, if it were x equals to the sine of y, now I can integrate the sine of y with respect to y, and I know what that is, right? So that's kind of another reason why. Maybe not as obvious. I don't know. But anyhow, that's why we have two different methods. I think I want to skip this one. This is a little bit more of a straightforward example compared to example 2. I'm going to try to, I know that probably didn't print out very well, but here in, this is, I think, blue. This blue line here is 8x. We'll call it, I don't know, put that purple line is y equals to x. And the red curve here, 8 over x squared. So these problems consist of, some of them have graphs, some of them don't. The one or two on the exam, make sure I put a graph. But just know if it's something like find the region between y equals 8x and y equals to x, you know, or sine, cosine, you should really know what those graphs look like. But the main idea is find the area bound by these regions, or these curves rather. And so the region that you want to find the area of, you've got to make sure that it's common to all of the curves or lines that they give you, right? So for it, what I'm saying is I don't want to find the area of this region right here, because the only curves that are binding that are the y equals x and 8 over x squared, okay? So I want to look for the area that's shared by all of those curves or lines, which is this area right here. So how much space do I have? So let me enhance that. All right, that may be too much. But that's the area, we're trying to find the area of that region right there. It's all right. So the first thing we really need to do is look at that and say, well, is it easier to integrate this with respect to x or with respect to y? What are you all thinking? X or Y. I heard both. In fact, in this example, I think it's about 50-50. Because when we look at 8x equals to y equals x, and y equals 8 over x squared, if I have to integrate that with respect to x, then I've got an 8x and an x and an 8 over x squared involved. No issues there. And if I had to integrate for y, those three equations are easily solved for x. Like I could say x equals to whatever pretty easily. So in all honesty, it doesn't matter if we integrate with respect to x or y. Either way you go, you're gonna see that if I integrate with respect to x and put in all of these rectangles running vertically, you see that there's a transition point. When my rectangles are vertical, it's the top minus the bottom, right, to determine the height. There's this transition point right here where, a transition point right there where the top and bottom are going to change. Really the bottom doesn't change, but the top function kind of shifts from the blue to the red, right? Okay. Similar issue if we're going to say, all right, well, maybe I want to integrate that with respect to y. My rectangles then have to run like this. But we also have that transition point where the right and left functions change. So we transition from the right function being purple to the right function being red. So either way, you've got that issue to take care of. Does that make sense? I think, if you draw these things out and draw your rectangles, I think that's, I don't know, maybe not for you, but I think that's a really crucial thing to do because it sets up everything for the problem. Am I doing this with respect to x or y? Is it top minus bottom? Is it right minus left? It all depends on how you're slicing, vertically or horizontally. So there's our transition point. And where, I'm going to again exaggerate one of our rectangles here. So we're fine up until we get to that black line, and then all of the rectangles over here have a different way to calculate their height. So we know here is the origin. This point right here is 0, 0. But what about the other ones? What is this point up here? And what is this point right here? So also with these problems, you have to determine where do these curves or lines intersect. You have to determine points of intersection. So this point up here, let me just label that point 1. Point 1 is just simply where the blue curve intersects the red curve. That's simply where 8x is equal to 8 over x squared. So I'm going to write here intersection. In most cases, you need the intersection points because those are what's going to go in for your A and your B, your alpha and your beta, your limits of integration. Okay. So we're going to multiply through by x squared. We have 8x cubed equals to 8, which means x cubed is equal to 1, which means x is equal to 1. All right, so therefore, the red and the blue curves intersect at an x value of 1. To find the y value, we can use either 8x or 8 over x squared. So we have the x is 1, the y is 8. Since we are integrating with respect to x, which is right here, this thickness here, we're integrating with respect to x. Really, you don't need the y coordinate of the points because everything we do is in terms of x. All right. So again, if we just look at that graph, we know that these points intersect here at 1. So that intersection point is at this x value here of 1. Is what we found. Okay, we'll call this point number 2. Find the intersection there. That's when the red meets the purple. 8 over x squared equals to, what was that, x? So that's when 8 equals x cubed. X equals to 2. So this is the point 2 comma what?
2.
2 comma 2. It's on the line y equals x. Okay. If you've got to integrate with respect to x and y, then yeah, I would recommend finding both coordinates of the ordered pairs. Okay. So then, what do we have to do now in order to find the area of this region? What does the setup look like?
You find it from 0 to 1 and 1 to 2.
Right. Yep.
With respect to x.
Yep. So we're first going to find the area of this region, and this goes from an x value of 0 to an x value of 1. So we're finding that area. So let's write that out. The integral from 0 to 1. Remember, since the slices or our rectangles are running like this, the height is determined by the top function minus the bottom function. So the height of all of those rectangles in that region up to the line is defined by 8x minus x. Just write that here. 8x minus x dx. Of course, we could simplify that, but we'll just write it like this for now. I'm going to put the colors back in. All right, so that's kind of like maybe a little more than half of the region. What else do we need to do with that?
Add From 1 to 2.
Yeah, so we're going to add the other area to it, which is found by taking the integral from 1 to 2, an x value of 1 to an x value of 2. And then what's our integrand?
E over x squared minus x.
Top minus bottom. Again. Okay. So that's the setup. Is everyone okay with how we arrived there? All right. We're not going to integrate this all the way, but this is 7x. In preparation to integrate 8 over x squared, as a reminder, those kinds of things, I want to write that as 8x to the negative 2, and then that way we can use the power rule. So the answer is 6. Yeah.
So I accidentally didn't see that you can subtract 8x minus x to 7x, but I still got 6.
Yeah.
So like, is that okay?
Yeah,
Okay.
totally fine. Remember the antiderivative or the integral works across sums and differences, so you'd get the same result if you forgot to combine like terms. It's just that you had an extra term that you had
Yeah.
to worry about, but that's not a big deal. I say the less terms, if you can, just combine them, because the less things you have to track, the better. Less likelihood there is to make a mistake, but yeah. Okay. Questions on that example? If you're looking at this and you're really not understanding it, then just please ask, because honestly, when we get to 6.3, it's going to kind of take off of this right here, because then we're calculating volume in 6.3. So if the two-dimensional area case is kind of funky for you, then more than likely the volume will be a little bit more difficult. So just ask if you have any questions. I think we'll take a break. Again, we'll not finish all of these examples, but I at least want to look at 2 other ones. One that's kind of more in line with a homework question, and then maybe have you all do one by yourselves. All right, so 10 minutes, and then we'll continue this section. I did. No, I'm going to do that after break, though, for sure, because I totally forgot. Under handouts, it's called 4.9 integral formulas. So it's all the integral formulas up to this point that you should know. They present this in terms of derivatives first, because really, remember, the antiderivative was the reverse. It says antiderivative of this function. We think about, well, what function did I take the derivative of to get the thing in front of the integral? So the derivatives are presented first, and then the antiderivative. So it does look like a bit much to take in, but all the antiderivatives are kind of on the right. Let's go ahead and look at this problem. So we're going to find the antiderivative of 7x. So we're just going to add 1 to the exponent and divide by the same exponent. We have 7/2 x squared plus, or rather, evaluated from 0 to 1. And then we have the 8x to the negative 2. You know, and maybe the way we're thinking about this is the constant comes out, we're integrating just x to the negative 2. minus the integral 1 to 2 of x dx. Okay. So we have 8, add 1 to the power, divide by the same result, and add 1 to the exponent, divide by the result. And then this one, evaluated from 1 to 2. So the only time the power rule fails is when we have to integrate x to the negative 1 with respect to x. It's the only time we can't use the power rule. You divide by 0, it doesn't work. You just have to know that the antiderivative of 1 over x is,
Natural log of x.
yeah, that's the natural log. And we actually write natural log absolute value of x. Because the derivative of the natural log of the absolute value is still 1 over x. However, if we look at 1 over x as a function, it looks like that, but the natural log has an asymptote here, looks like that. So the reason we have the natural log of the absolute value of x is so we can also include these negative numbers over here. We still can't include 0 because it's our asymptote, but it allows us to put negative numbers in here just so that those two functions domains are more consistent. Okay, so that's the only one the power rule doesn't apply to. Again, that's something that you should know. So these types of problems, especially when you have to separate them, they can get pretty tedious. You know, if you've got 3 or 4 different regions you've split up, depending on the function, you might have like 5 terms in there where you have to plug in 0 and 1, and then 4 more terms to plug in 2 and 3, and then 4 more terms to plug in 4 to 5. So they can get pretty tedious, which just means there's a lot of opportunity to, you know, forget a negative sign or do something like that. Okay, so 1's going into 7/2 x squared, and we subtract off the lower limit into that function, plus this one's going to get a little lengthy. We're plugging in 2 and this f of b minus f of a. And then so once we, you know, you do want to make sure that you're keeping things together, because we have to take the upper limit and subtract off the entire lower limit. And especially if you have multiple terms in there, it's really easy to forget a negative sign or something like that. So once we compute all of that, you should come up with 6. Are there any questions on that example? All right. I don't know if that's not showing up too well. That purple curve is the y cubed minus 4y. And see, that's defined as g of y. You know, we could call that x, just like we call y equals to like square root of x, f of x. And then this function is the other one. Y cubed plus y squared plus 8 equals x. Okay, so notice it says find the area of the region bound by not only those two graphs, but it says for y between -2 and +2. So here's our y equals to -2, and here's y equals to +2. So the region we're finding the area of, just think about it, it has to touch all of those things. So we're finding the area of this region right here. So here's a perfect example of why it's beneficial to have kind of two ways to look at it. If we tried to do this, or find this area with respect to x, you know, then like even here, there's an issue. Like that rectangle, we have to calculate top minus bottom, which means we have to take this equation and solve it for y. Right? We know that if it's quadratic, then there's a formula that solves for us, right? There's a quadratic formula, but there is a cubic formula, but if you saw the formula for it, you wouldn't want anything to do with it. It's hideous. And then there is no 4th degree, 5th degree. There is no known formulas for those. Point being, we don't want to take, you know, either one of those equations and have to solve for y, because then we're solving for a cubic. So it's much more easy with something like this to say, well, what if my rectangles are running this way? Does the right and left ever change? All throughout that region, it's right minus left for that height, right minus left for that height. Those never change through that region. And again, since our rectangles are running horizontally, we're thinking about them starting here at -2 and then running up to +2. So if we can leave everything in terms of y, because these rectangles that we're looking at horizontally do have thickness or length dy. So everything can be in terms of y if we orient it that way. So the right minus left never changes. Like in that previous example, the top and bottom, top minus bottom changed, so we had two different integrals. Here we're just going to have one integral from a y value of -2. Because again, does everybody see that? Our rectangles are running like this, from -2 all the way to +2. And it's the right function minus the left function in terms of y. So don't forget to subtract off the entire function. Don't just subtract off one part of it. So that's the setup for the area of this region. Does anyone have any questions? And then here you can integrate each term, but I think it's easier to just combine like terms first. So we're going from -2 to 2. The y cubes go away. We have y squared. We have a minus 4y and a +8. So hopefully you can get that to come out to 112 over 3.
So the two curves touching at the end doesn't matter.
We're at
Whether
the
or not
end.
they do. At like -2 and 2. They don't have to touch for it to work.
Oh, right, they don't have to touch, because it says find the area bound by these things. Any other questions? Does everybody have what they need? All right. So I know I said I'd probably let you work on one. Honestly, we've got to move a little bit quicker to get to start 6-3 today. I hope, like I said, some of this is review. If not, not much we can do. Okay, so the area of the region bound by the natural log of x, y equals 2, y equals 0, x equals to 0, by setting up an integral with respect to y. Okay, so let's just draw our, so 2 is the biggest one we have. Let's do each tick mark as 2 units. So there's the natural log. Y equals to 2. It's up here. Y equals to 0 is here. And x equals to 0 is here. So I probably didn't draw that out far enough. If you remember the graph of the natural log, it kind of slowly creeps up, but very, 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 very slowly. So I'm just going to exaggerate that a little bit so we can all fit it here in this window. Just enlarge that region here. So that's the area we're dealing with. If you wanted to get clever and do the area of this rectangle plus the area of this region, it's the same thing. A lot of people look at these regions in a different way, and it's fine. Even that first one we did, I think at least one person took like a couple of areas and then subtracted off another one to get the area we needed. There's really no right or wrong way to do that, assuming you're doing it correctly. I know that seems like an obvious statement, but okay, so we have to find the area of this region. Notice it says set up an integral with respect to y. If we're integrating with respect to y, what direction are the rectangles running? Horizontal, right. So what happens if we tried to set up with respect to x? Can we do top minus bottom here? Yeah, it's just 2 minus 0. What about top minus bottom here? It's harder in the sense because the top is 2 and the bottom is the natural log of x, right? So there's nothing wrong with that function, but we have to remember we have to integrate that. So how do you integrate the natural log of x? We don't know how to do that yet. So if that was our approach, we would say, well, that's giving me a problem. Maybe if I look at it the other way with respect to y instead, it might yield a simpler integral or antiderivative. Okay. So with respect to y, here's our rectangle. Does the right minus the left ever change through that region? Again, y ranges from here all the way up to here. Y ranges from 0 to 2. The right function is always, let's write this out, the right function is always ln of x. But are we just going to throw ln of x in here? Since we're integrating with respect to y, we need to solve ln of x equals y for x. So we have a function in terms of y, not x. If the natural log of x is y, what does that mean x is equal to? E to the y. So I want to put e to the y here, not ln of x. There's the right function. What's our left function?
Y equals 0.
Y equals 0. So I mean, if we want to see that, we'll just write it here, but it's not necessary to put minus 0. So, okay, to find the area, we just integrate from 0 to 2 on e to the y with respect to y. What's the antiderivative of e to the y with respect to y? E to the y. Evaluated from 0 to 2. So we have e squared minus e to the 0, which gives us e squared minus 1. Okay, questions on that? I'll skip this next example. It's a good example to look at because, like one in your homework, it says to set up this region and then find the area by integrating with respect to x and with respect to y. So sometimes we can do both. If you want to work through this, let me just go ahead and write this out. With respect to x, you should end up with the integral from 0 to 1, rather, square root of x minus x cubed dx. And if you integrate with respect to y, you should end up with the integral from 0 to 1 of the cube root of y minus y squared dy. And so as a reminder, whenever you see roots like that, you want to turn them into powers, because it's all of those funky roots are always just powers of x or y, and use the power rule. Okay. So you got to graph those two functions, find their points of intersection, should be able to do that, and then set up this one's top minus bottom, this one's right minus left. If you work any of these that we don't get to in class and have problems, ask. I'll be happy to go over them in class. Okay, does everyone have what they need from this, or do you need some more time? I want to look at number 7. There are some identities here in 6.2 that I'll write down that you should, trig identities that you should remember and are pretty necessary for getting through some problems. And some trig identities we'll see over and over and over again. Other trig identities we'll never see. And a couple of trig identities we might see once or twice. But some of the main ones are in this section that we see over and over again. Okay, so we have, let me draw this in different colors here. Oops, as close as I can. So that curve is sine x or sine 2x? Which one? Okay, does that look right? Sorry that you can't make these numbers out. This might help. This right here, this value is pi. Of course, if we said find the area bound by sine and sine 2x, that would be like, that would be a exercise in futility. because you can't do that. They overlap and intersect forever. So we'll just stop at pi. But knowing that that's pi, not 2 pi, does that change our... Yeah, so the red curve is actually sine then, and the blue is sine 2x. Okay. So using the most efficient method, set up the appropriate integral. So we'll set this up. Well, what's the most efficient with respect to x, top minus bottom, or with respect to y, right minus left? With respect to x. So even though the top minus bottom here to here changes, if we integrate with respect to y, then I have to integrate x equals inverse sine of y. Again, I don't want to integrate inverse sine. So dx with respect to x is the most efficient. Later, I think it's 8.2, we can integrate inverse sine, but it's still not as simple as integrating sine. Okay. So we've got to, we see this transition point here. We've got to find that intersection. So it doesn't matter where you set this, how you set this up. Eventually, you're going to have to find the intersection points anyways. So it doesn't matter when you do that. So let's find those intersection points when sine of x equals to the sine of 2x. Oops, I wrote that wrong. Different colors anyways. So when does the sine of x equal sine of 2x? There's just one identity here you have to remember. The identity for sine of 2x so if you don't remember that, do you remember the identity for the sine of a plus b? Because that's where this identity for sine 2x actually comes from. No? Okay. All right, so here's a good refresher then. The identity for sine of 2x is 2 sine x times cosine x. That's a super common identity. So is the identity for cosine 2x, and there's 3 of those. All right, so we don't want to just divide out sine because sine x could be 0. And in fact, it is 0 in this region, right? So we can't divide, we can divide, but we have to consider 2 cases, when sine x is 0 and when sine x is not 0. So let's just not even do that. Let's just get everything on one side and then factor out the common factor. Factor out sine x of 1 minus 2 cosine x. So now we've got 2 things multiplying, giving us 0. So we can set each one equal to 0. When does sine x equal 0? And when does 1 minus 2 cosine x equal 0? So sine of x is 0 when x is 0, when x is pi. I mean, we could keep going, but everything else is outside of our region because we're only considering the region from 0 to pi. Okay, looking at the graph, you can see what those values contribute to. We found this intersection, and we found this intersection. So 1 minus 2 cosine x. When does the cosine of x equal to 1/2? The other one.
Pi over 3.
Yeah, pi over 3. And where else? So 2 pi over 3 is in the, 2 pi over 3 is over here. X is, cosine is negative over there. Yeah, 5 pi over 3. Do we need to worry about that? 5 pi over 3 is over here. Remember, we're stopping at pi. We're stopping here. So we just want those. We don't want that. So that intersection that we drew the solid line at, that intersection is pi over 3. All right, Mike, I'm gonna let you reference the graph. Someone tell me what the area would look like. Maybe someone that hasn't spoken but wants to. If not, feel free to shout it out. So the first region, we go from, okay, from 0 to pi over 3.
Sin x minus 1 sin 2x.
Okay. Do you all agree with that for the first little piece? Yeah, so dx, top minus bottom. Top is blue. Sine 2x minus red. Right. Okay, sine 2x minus sine x. That's weird. Okay, and then what's next? Okay.
And sin x is minus sin x.
Okay, sine x minus sine 2x dx. What do y'all think? Okay. All right, there's the setup for the area. Sine 2x is, I think maybe initially when you saw that was a u substitution. Really, I think at this point, or at some point in the very near future, when functions have linear arguments like that, mx plus b, you should be able to find the antiderivative without doing u substitution. It's not that using u substitution in instances like that is bad or wrong. It's just that it's not as efficient. Okay. So, because then you have to say, okay, I'm going to let u equal 2x, then du is equal to 2 dx, and so it's 1/2, right? You have to do all of that kind of stuff. Where if you just know, like when I take the derivative, like if I took the derivative of sine of 2x, I would say it's the cosine of 2x times 2, but keeping in mind that the antiderivative is reversing that. Instead of multiplying by that linear argument, its derivative 2, we're just going to divide by the 2 instead. It's really the only difference. So what is the antiderivative then of sine 2x?
Negative 1/2 cosine x.
Yeah.
2x.
Negative 1/2 cosine of 2x. So instead of multiplying, we're dividing. It's the antiderivative. I think there's also confusion because the derivative of sine is cosine. The derivative of cosine is negative sine. But then when we look at the antiderivative, those negatives change places. Antiderivative of sine is negative cosine. The antiderivative of cosine is sine. Okay. Minus the antiderivative of sine. What's the antiderivative of sine? Negative cosine, right? So that turns into a positive. And like was mentioned in Calc 1, the nice thing about antiderivatives is you can always check your work. If I take the derivative of cosine, I get negative sine, so that's the correct antiderivative. If I take the derivative of the cosine of 2x times negative 1/2, that's sine of 2x times 2 times the negative 1/2, or sorry, negative sine 2x times 2 multiplied by this negative 1/2 gets me back up to my positive sine of 2x. So you can kind of hopefully quickly check, assuming you're familiar with derivatives, which hopefully you are. That might have been a longer time ago than antiderivatives even. Okay, so those two are evaluated from 0 to pi over 3. It didn't say evaluate this, but I just wanted to talk about this. So here, derivative of sine minus cosine, and again, the derivative of minus sine 2x, that's going to be what? Minus sine 2x. The antiderivative of minus sine 2x. Yeah, positive 1/2 cosine 2x, and those two are evaluated from pi over 3 to pi. So even something like that is a bit tedious to compute those values. So are there any questions on that example?
First half 0 to pi over 3, right? Not 0.
Yeah, 0 to pi over 3 for this one. Yeah, thanks. All right. Well, so does everyone have what they need from that? I need to skip ahead so quickly. All right, just a summary here. So the one identity we've seen that we'll need is for sine of 2x as 2 sine x cosine x. The other one is for cosine of 2x. Does anybody remember either one of those three? Cosine 2x?
Cosine squared minus sine squared.
All right. Cosine squared minus sine squared. If you can remember that one, then you can get the other two, assuming you remember. Do y'all remember the Pythagorean identities? So the other two come from the Pythagorean identity. Sine squared plus cosine squared is equal to 1. And that's just the unit circle equation, right? Because the sine was the y coordinate, the cosine was the x coordinate, and there we have equation for our unit circle. So in order to get the other two for this, if you forgot, then I guess this is a long-winded way to get there, but hopefully at some point at least one of these identities will be like, oh yeah, I remember that one. You solve for cosine squared in this one, and then put it in here, then solve for sine squared and put it in there, and you'll have the other two. We have 2 cosine squared minus x minus 1, or 1 minus 2 sine squared x. So either of those three valid representations for cosine 2x. The other two things you should know, and that do come up in this unit's homework, is really the identities, but for finding the antiderivative of sine squared and finding the antiderivative of cosine squared. But those just involve, if you have to find the antiderivative of either, it just involves the identity we'll write down. So Sine squared x is 1/2 times the quantity 1 minus cosine 2x. And cosine squared, we use 1/2 times 1 plus cosine of 2x. So all of these identities are extremely common. I would say you need to know the basic trig identities, because all of the other identities that are more obscure are based on these. All right. So really, the first two are primarily involved when you have to solve trig equations. The sine squared and cosine squared identities are involved for finding the antiderivative of sine squared and cosine squared. And those two, sine squared, cosine squared, the integrals of those are pretty common. So they come up a lot. You want to know how to do those. All right, that's it for 6-2. If you can, try to start on the homework for some of this stuff. If you run into any issues, you can email me, or I'll be happy. If you don't want to, say in the middle of class, hey, can you do homework number 5? Then just email me before class and say, would you mind working homework number 5 in 6.2 in class? I can't work all of them, and most of them I might not work fully, but we can at least talk about like setting up or whatever the issues are. I don't mind.
Question for you real quick. When
Sure.
will you have the video for this stuff? I gotta leave just a little bit.
Okay.
So I'm gonna miss this last part.
Yeah, probably not till Monday,
Okay.
because I'll convert it tonight, but I won't be back till Monday.
Okay. No problem.
Yeah.
Thanks.
I'll upload the notes though.
Okay, yeah, I'll take that.
All right, cool.
Thank you. See you guys Tuesday.
See ya. Have a good weekend. All right, so 6-3, we're moving into determining volumes. There's really 3 things that kind of build on in this section and in the next section. The first thing we're going to look at is this general slicing method. Then we'll look at disk washer method, also in 6.3, and then we'll look at the shell method in 6.4. So all of these methods enable us to find volumes. So let's start with some like basic figures and say, how do you find the volume? Let's start with this cylinder here, this right circular cylinder. How do we find the volume of that?
Pi r squared height.
Yeah, pi r squared times the height. But if we kind of think of it in a different way, it'll be a little bit more advantageous to us when we look at the formula for finding the volume by slicing. Okay, so let's say I'm only going to consider this circle whose area is pi r squared. And then since it's a nice figure, or symmetric figure rather, I can take this circle and extend it. We'll call this h. This length here is h. So I have an area times a linear that gives me 3 dimensions, that gives me a volume. Okay. So volume is pi r squared times h. How about the right triangular prism? What's the area? What's the volume of that? Yeah. So we'll just consider the area first. And so that's kind of our approach to finding volume, is we'll see all these complicated figures. We don't want to think about the volume. We want to think, all right, well, what is the area of this slice? And then I'm just going to extend it, from A to B. It's a little bit more involved than that, but that's the idea. So here's the area as 1/2 base times height. We'll say that's base, that's height. And then we'll just call this whatever, length, width, etc. So the volume of this thing is 1/2 base times height times length. And for the rectangular prism, same idea. Just going to compute the area of the space here, area. It may not be a square, so we'll just say area is length times width, where this is L and this is W. And call this, I don't know, H. So that's our volume, area times H. That's kind of the main takeaway. Volume is area times a linear measurement, or a linear dimension, whatever that is. Okay. So notice what's true about all of these figures is that no matter where I cut into them, that all of the cross sections for this piece right here, if I cut into it like that, you know, that's going to be the tiniest cross section that looks like this, right? It's still the same shape. If I cut into my cylinder, no matter where I cut into it, all of the cross sections are going to be circles. It's a terrible circle. If I cut into this, everything is a rectangle. So the idea is like, all right, well, how do we find the volume of a loaf of bread? We're going to take the loaf of bread and we're going to cut it up into super thin pieces, and we're going to calculate the area. But the nice thing for us is we have nice figures with respect to an area. We're not going to have this crazy thing right here, but we calculate the area of its face, and then we just multiply through by whatever this is. Yeah, I'll mention that later. So it goes back to the general slicing method, which says, you know, if I have this weird saddle looking thing and I want to know what's the volume of it, then I'll say, well, if I cut into this thing, what do my cross sections look like? And then I'll just multiply the area of each cross section by its thickness, which will give me a volume. So I'm going to just multiply this by its thickness, and then that'll give me the volume of this solid here. And I just add all of those up. So that's kind of what's illustrated here. It starts off pretty blocky, but then when we let the number of cross sections or slices approach infinity, then we have a complete volume, an accurate, exact volume. But again, what we're starting with is the area of each cross section. We're summing those up. So that's the area of the cross section. Has an area given by A. So cross-sectional area. And then our dx is just that really thin thickness, right? So we have an area times thickness, it's a volume. So remember, the integral is just a fancy infinite sum. We're summing up area times thickness. We're summing all that up, which gives us volume plus volume plus volume. Okay. But what's important here in this initial setup is that the area, A of x, the area is a function of x or y, but it represents the cross sections. Does that make sense? Is that easy enough to follow? It's harder to put into practice, but that's the basic idea. And I don't know, to me it's super cool that you can calculate a volume when all you really have to worry about is an area. It makes things a lot easier. So we're going to look at this problem. The slicing method to find the volume of this solid with a circular base of radius 5. whose cross sections, that's where we're taking our clues, like the A in that previous integrand, again, was the area of the cross sections. So that's what we got to start off finding. That's the function we are integrating, is the area. So whose cross sections that are perpendicular to the base and parallel to the x-axis are equilateral triangles. Okay, so we've got this circular base, but we say, like, you know, I don't know, maybe we have this weird knife that we're cutting through, and every time we cut through, it makes a triangle in that. Okay. So there's one slice into that region. What we're doing is we're filling that entire region up with these. And notice how the equilateral triangles change because the length of the base changes. Here it's maximum at 10, right? Because it's a radius of 5, so we have a base of 10, height of 10, sides of 10. But then they get smaller as we get more towards this edge. So here's the figure that if we actually fill that region up with equilateral triangles, we get that region right there, or that solid rather. So the trick is here not to even think about the three-dimensional shape that's generated. It's to solely think about what are my cross sections and how do I find their area. So let's translate this maybe into a more, you know, they have x here and y here. Let's translate this here as y, and this is x. Just a more familiar setting. And we're told that our cross sections are parallel to the x-axis, meaning the slices or the rectangles are running parallel to the x-axis. So that means we're going to that means we have to integrate with respect to x or y. Right? Because remember, we're envisioning that this is my cut, this is my rectangle. It has this tiny thickness here, dy. So bounds need to be in terms of y, and we need to have the integral of, you know, like y squared plus y or whatever. Okay. All right. That's really step one. Here, then determining, all right, well, I'm told that my cross sections are equilateral triangles. So let's just write that out. The area of triangle, all triangles, is 1/2 base times height. But knowing that I have to put that in front of an integral, and it has to have y's involved, right? What do I have to do here now with this 1/2 base times height? We have to have a base and a height that are
In terms of y?
that are in terms of y, yeah. So we need B and H in terms of y. Because we saw with that interactive figure that the base, which is directly related to the height, that changes depending on where you're at on the circle. Down here, whatever, draw this tiny little triangle here. There's our slice right there for this one right here. We have this triangle here. All right. So it's an equilateral triangle. Would it be easier to find the base of the equilateral triangle first or the height?
The base.
The base? Okay, so let's find the base. So the base. What's the length of the base?
2 times the square root of 25 minus y squared.
2 times the square root of 25 minus y squared. What do y'all think? Not sure. How do we measure this length that's running like this? It's the right minus the left. Just like it was in 6.2, how do we measure that variance or that variation? It was always this function value on the right minus the function value on the left. So again, if I'm here or if I'm here, that length is going to vary depending on the boundary of that figure. Those boundaries change from problem to problem too. But the idea is that, I'll keep it green, but the idea is that this length here is just the right minus the left. If we were slicing parallel to the y-axis, we would say the length of each equilateral triangle is the top minus the bottom, right? So that's consistent through this section too. The thing is we have to find what is the right and what is the left. But again, this dy tells us everything needs to be in terms of y. We have to solve something for x. So what we're dealing with is the circle of radius 5. So we can write the equation out for the circle of radius 5. But since I'm integrating with respect to y, I need to solve that for x. And so when x is the positive root, we have this part of the circle. Sorry, this might look, it's getting a little disorganized. And then the negative square root is when x is negative, which is the left half of the circle. So we have the right is positive root of 25 minus y squared minus the left, which is the negative root of 25 minus y squared. So we have root plus root. We have 2 of those. Are there any questions on that? So naturally, like if that's all you have to find is the area function, these problems are hard because you gotta write sometimes several variables, length, width, whatever, in terms of x or y, really. So there's our base. Any questions on how we got that? Again, everything hinges on how our slices are running. Okay, we've had the base. Now we need h in terms of y as well. How are we going to do that? Give you a hint. They're equilateral triangles. I know that's stated, but
Can you just like, isn't it the square root of 3 over 2?
Right.
And then just square root of 25 minus.
well, so say that again.
So
root 3 over 2.
Yeah, it's the side line. So you're gonna cut the base in half. So
Yeah.
you're just looking at half of it.
Right.
So it's a 90 something, 45, 45.
Uh-huh.
And then, what was that? I forget.
That's
The-
for,
the
yeah, you're
special
thinking about if the
triangles.
base is length 1, it's root 3 over 2
Yeah.
is the height. But you're on the right track. So we have this, you know, our equilateral triangle. And again, that when we're looking at it dead on like this, the apex is like here, right? So we're looking down on it. Anyways, the idea is that we've measured this base. We know what this base is as a function of y, which means that this side is length b, this side is length b, equilateral triangle. But what we're going to do is drop this perpendicular bisector. And so we have this length still being b. This length now is half of what it was. And here's what we're trying to find. What is that height? With any triangle, or with an equilateral triangle rather, there's always a specific relationship between, a fixed specific relationship between the base and the height. And, you know, I don't want to go through all of the algebra that's here. But from this point, we're just going to utilize the Pythagorean theorem and solve for h. So any equilateral triangle, the height is always root 3 over 2 times the base in any equilateral triangle. Okay. So since we now know that h is root 3 over 2 times the base, we already know what the base is in terms of y, therefore we can put h in terms of y as well. So that's root 3 over 2. Let me write this in a different color. Times the base. And from the step above, we saw that the base was 2 times the square root of 25 minus y squared. So that's our h in terms of y as well. Let's simplify this a little bit. Okay. It's already pretty involved. We don't have much time to finish, but we can now set up the area function and integrate that to get the volume, okay, which we'll do next class. Are there any questions before we take off? All right. So please, if any of this you have issues or questions with, email me, and we can talk about them on Tuesday.